Hello. Let us understand the question first. Let x be a metric space and x0 be a fixed point. Show that the function defined by a metric is uniformly continuous on x. So this is the definition of uniform continuity from the textbook of Tosun Terzioğlu. But before starting, let us observe something. Observe first that for any x and y in the metric space x, since it's metric, its metrics should satisfy the triangle inequality. So we have dx y less or equal to dx z, let me put z also, plus d z y. So we can also rewrite this in the following way: x y minus d z y less than or equal dx and z. So this is by triangle M3 inequality, etc. So after observing this, let us start proving. Given any epsilon bigger than 0, choose delta to be something if dx y is less than delta for x y in x. Okay, then f of x minus f of y, I mean d of x x0 minus d of y x0. Okay, I need to show that this is less than epsilon, but it is true because I can rewrite this as, okay, this part as d x and y by this above observation. Okay, or I can rewrite this as less than dx and y. Okay, let me put it in this way. Okay, in this observation, if I choose this delta to be exactly epsilon, then everything should be fine, right? Okay, given any epsilon, choose delta to be epsilon itself. If dxy is less than delta, okay, then this thing or this thing should be less or equal to dxy, and then since it is delta by hypothesis and delta is epsilon, then we are finished. Okay, so this is a valid proof. It's very easy proof, but yeah. So let's understand the second question. Let A be a subset, be subsets of R, and let's define the summation of two subsets of R as follows. If A is open and B is any subset, then A plus B is open. The hint is given by the following data: A plus B. Write A plus B as this union, which is of course true. Then show that B plus A, okay, maybe let me write in this form. Okay, A plus B. Okay, then if you, this is trivial, if you can show this is also open, then we are finished. The main idea in this question is the following: since A is open, then A plus B is just shift. Okay, A is, for example, this is R, A is here. Okay, A is the union of open intervals, obviously. If you sum with B, you are just shifting right or left. As you can see, shifting open sets are, preserving the openness, so we will get the result. Okay, let me prove it. Following the hint, answer, let's the hint given, okay, A plus B is open for any B in B. Okay. Given any B in B, and given any A0 plus B in A plus B. So I'm gonna find a neighborhood around this point such that it is completely inside of this, which proves my point. So since A is open, there exists open neighborhood of A0, which is, for example, say A0 plus, not minus, epsilon, A0 plus epsilon inside A. Okay. Now, so trivially, this is also a neighborhood of, okay, so obviously, I don't like this word, but yeah, in this case it is really obvious. A0 plus B minus epsilon, A0 plus B plus epsilon is also contained in A plus B. Okay. So we have found an open neighborhood of A0 plus B in A plus B. So A plus B is open, and as you can see, A plus B can be written as union of B from B, A plus B, right? Okay, let me prove it. This is trivial. This can be shown as given A plus B in A plus B. Now, okay. Now, of course, this is also true. A plus B in A plus B. So, check that. So it is already trivial, but I had a feeling that I need to prove it also. So these are all open sets. And any union of open sets is open. So A plus B is open. This is our third problem. Let X be a metric space and E be any subset. So the closure of A can be also defined by the following axis from the metric space such that the distance from X to the set itself is 0, where this distance is defined by this infimum of dxy's, where y's are from the set. So let us show first the following inclusion. E is subset of right hand side. Given any E from E closure, or let me use X. Okay. Then, by definition of closure, for any epsilon bigger than 0, the ball centered at X with radius epsilon intersect with A is non-empty. Now let us try to show that this X is indeed in this set. So we aim to show dx e is 0, okay, by using the definition of infimum, by using infimum. Okay, so given epsilon bigger than 0, so no, let me just first use show that it is an lower bound. Okay, it is lower bound. 0 is the lower bound for the set dxy where y is from E. It's trivial, right? Because trivial by definition of metric. Since for every xy, dxy is bigger than 0. So they are bigger than 0, so 0 is lower bound. So now use the now satisfy. Let us try to check the second part of the definition of being an infimum. So given any epsilon bigger than 0, okay, we try to find dxy0 in the set dxy's such that dxy0 is less than epsilon plus 0. This is literally the definition. Okay, that's why I'm writing this tedious calculation or statement. So but by the definition of by above def bx epsilon intersect with E is non-empty, so there exists y0 in E such that dxy0 is less than epsilon, because there exists some y in E, okay, that this is non-empty implies there exists some point inside of this E such that it is also in this ball. That's why this is satisfied, okay, because every point in this ball satisfying dxy less than epsilon. This is the definition of being a ball, okay. That's why we have such thing. But as you can see in this parenthesis, we try to find some dxy0 such that dxy0 is less than epsilon, so it is finished. Now let us try to show the other way around. E closure is bigger than right hand side. Okay, given any x in the set x of x dxe0, then again using the same idea, okay, we have dxe is 0. So this is an infimum, as similar to the first part of the proof. So there should be some y0. So by using the definition of infimum again, there exists some y0 in E. No, again, for any epsilon bigger than 0, there exists y0 in E such that dx y0 is less than epsilon. It means y0 is in this ball bx epsilon, right? Because this is equivalent definition of y0 being in this ball, but y0 is already in A, so y0 is already in E, so it is in this intersection of this ball with E. So this is non-empty. Proves that y0 is in no. It proves that since epsilon was arbitrary, x is in the closure of E. That finishes the proof. Okay. So let us understand the problem. Let X be a metric space, U be an open subset, show that U is a countable union of closed sets in X. Okay, if U is empty or U is the whole metric space X, we are done. Since each empty and whole space are closed, so we are done. So if not, otherwise, consider ANs or define EN to be the union of y in U complement b y 1 over n. So we are considering balls centered at y and radius 1 over n, and I am uniting every such points when my centers are outside of the open set U. Okay, so let me give you a picture so that we can maybe understand. So let me call this is my U. Let us call this is my U. So AN should be considered as the union of the following open balls. So for example, I am taking this Y. So I am considering a ball around Y with radius 1 over n. For example, I can also consider another ball. I can consider another ball. But as you can see, each center are outside of U. Okay, I can consider another ball, etc. So they are corresponding to this union AN. So my claim the U is just the union of complements of ANs, n equals 1 to infinity. So answer, let us prove it, or proof. First, let me show this U is subset of this infinite union. By the way, this complement means, okay, where A and C means X minus AN. Okay. Okay, if you don't recall. Okay, here is the proof. So let me show this direction. Given any u from this u. Okay, since u is open, there exists a ball bx epsilon such that it is entirely in u. Okay, it means that if u is a point inside of this bigger u, there exists a ball. Okay, maybe this is too close to the boundary. Let me put it here. U. There should be a ball around u such that it is entirely enclosed in this bigger u. Okay, it is my ball. Now I'm gonna use the following Archimedean principle by Archimedean principle. There exists is a natural number n0 such that n0 is bigger than 1 over epsilon. Okay, or epsilon is bigger than 1 over n0. Since everything is positive, I can do this following, and everything is not zero. Okay, what's my point? Let me explain my motivation. Since I am uniting, for example, this is an, right? I'm at the end, I'm uniting an complements. So my ball is here, so I'm gonna find that this u is not enclosed by an for some n. It means that this is not encircled by an for some n, right? If n is big enough, this is guaranteed, right? If n is big enough, or this 1 over n is small enough, then any ball here outside of this u cannot encircle u. I am searching for this kind of u, and it is exists by Archimedean principle. If I can do it, then I can show that this u, this little u, is in some an's complement, and this is proven, right? If u is here, if I can find some an complement, then this is proven. By the following data, it is already shown, but let me show it. So, hence, x is not in b y 1 over n0 for any y outside of this u. because it seems a bit repetitive, but because dx and y would be bigger than epsilon, right? This is because for any y outside of this u complement, or x minus u, right? Because this ball is entirely in this bigger u, and if I take any point outside of this u, okay, let me also call them purple. If I take any point outside of this bigger u, the distance between little u and this y should be bigger than epsilon, because this little u is in this little ball which has radius epsilon, right? By definition, their distance should be bigger than epsilon. Okay, that's important. And this n0 is absolutely less than epsilon. So and epsilon is bigger than 1 over L0, so X is never in these kind of balls. Okay. So that's the explanation. Let me put a parenthesis. Okay. Now, if it is not in this kind of balls for any y, it means that so X is in not in the intersection of B, Y, 1 over N0. Y is outside of this U complement. But by definition, this is just the complement of AN0. Right? Because, let me calculate somewhere. AN is by definition the union of Y in U complement, B, Y, 1 over N. And if you take the complement of both sides, by De Morgan law, it gives you this intersection, since U complement B, Y, 1 over N complement by De Morgan law. And there should be some corrections. This should be union, this should be AN, because I'm talking about not element, okay, not being inside, so this is true. So X is not contained in any ball. It means that it is not also in the union, but this union is equal to AN by definition. It means that X is in the complement of AN. Okay, so X, let me open parenthesis and close parenthesis. This explains this, and this explains the following. X is in AN complement. Since AN is a union of open balls, which is open, so AN is open. So what is the complement of an open set? Closed set. So X is one of the closed sets, and so it is in this union. This is proven. This part is proven. I have shown that given any little u from this set, this little u is in this union. Okay, as follows. So this is proven. So let me make some space. Okay. So now let us prove this u is bigger or equal to this whole union, and goes to 1 from infinity to infinity, AN complement. Given any u in, not u, let me call it x in union of the following. So X in A and 0 complement for some A and 0 natural number. So it means that X is in not in A and 0, which is the union Y. I'm repeating myself, I know that. 1 over N0. So, or maybe it's not useful, or X is in the intersection of YU complement BY 1 over N0 complements. It means that X is not in BY 1 over N0 for all Y in U complement. So let me make some space to continue. Okay. So what's my point? My point is that I'm gonna show this X is inside U. Okay. But I think there is a shortcut. Let's observe something. Observe. I can rewrite this U complement as follows. Union vice being in UC and vice. Right? These are subset of union V's in U complement ball y 1 over n0. Right? Because the index are same, this each y is contained in this ball. So this inclusion is proper, and this is by definition. So it's correct. But as you can see, this x is not here. Right? By definition. Okay. By the way, don't consider this. This is extra information. We don't need that. The x is not in a n0. It means that it is not in this bigger set. Then x must be in U. And x is not in this U, y in UC, ball y 1 over n0. So x in U. Okay, that's more easy. Okay, that is finished. So I have just shown that the second inclusion is also true. So what did I prove? I proved that, oops, I'm messing with the context. Okay, I have just proven that my open set is union of, countable union of closed sets, because each AN is open, right? Because each AN is union, arbitrary union, not that arbitrary, but union of open sets, which is open. And I'm taking the complement, so each thing is closed. And I've just shown that these two things are equal. They are equal. So it means that any open set is a countable union of closed sets. It is finished.